Alright, a 3 kilogram book is lifted straight up. How much force is exerted? The equation for force, as top of force equals mass times acceleration. The mass is given as 3 kilograms, and acceleration is the acceleration due to gravity, which for all you physics people is 9.8 meters per second squared. So, simply enough, F equals 3 kilograms times 9.8 meters per second squared, which gives you the unit of newtons, and the math gives you 29.4. 29.4 newtons.
Go ahead.
Suppose a 1,258 kilogram elephant is lifted straight up 37 meters by a crane. How much work is exerted? Well, we start off with our equation of work is equal to force times displacement. And we have the displacement, but we don't have the force. So we need our force equation to calculate the force to use it. So force would be equal to the mass of 1258 kilograms multiplied by the acceleration due to gravity of 9.80 meters per second squared gives us a force equal to 12,328.4 newtons. So now that we have our force, we can do the work equation. So work is equal to 12,328.4 newtons multiplied by displacement, which is the 37 meters. And then that would give us, multiplied through, would give us a work of 456, 150.8. That's 0 Newton meters, which is the same as saying 456,150.8 joules.
Alright, a force of 2x cubed plus 8x newtons acts on an object. How much work is done in moving it from 3 meters to 7 meters? So in this situation, we use the variable work equation, which is shown right here, as the integral of a to b, which is the distance it is moved, so 3 to 7, of the force function dx. And the force function is given as 2x cubed plus 8x dx. So at first, we take the integral of this. So bring it up 1 power next to the fourth, and then you get 1/2 in the front, as 1/2 times 4 is 2. And then plus x squared, with a 4 in the front, because 2 times 4 is 8. After that, we have to evaluate this from 3 to 7. So to do this, plug in 7 into the whole equation. Which gives us 1200.5 plus 196. And after that, we must subtract after we plug in 3 to the force equation. So we get 1/2 times 3 to the fourth plus 4 times 3 squared, which gives us 40.5 plus 36. And after all this is calculated out, we get a grand total of 1,320 Newton meters, as meters and Newton are given in the equation. That is the work.
Alright, so a force of the square root of x plus 1 pounds acts on an object. How much work is being done moving it from 1 foot to 5 feet? Alright, so we have our equation. So by plugging these in, we'll get work is equal to derivative from 1 to 5 of our function. So let's rewrite this as x plus 1, 1/2 dx. This one we're going to have to use u substitution. So u is going to be equal to x plus 1, du is equal to dx. So that's good. So then if we run this through, this will give us u, like 1/2 du which then gives us 2/3 u to the 3/2. Let me plug u back in. So we get 2/3 times x plus 1 all to 3/2, and that's going to be from 1 to 5. Evaluated from 1 to 5. So then, try to do this. So 2/3 times 5 plus 1 to 3/2 minus 2/3 times 1 plus 1 all to 3/2. And then if we run that through, we get 9.798 minus 1.885, which gives us a work equal to 7.913 foot-pounds in the U.S. system. And there you have it.
Alright, a force of 100 newtons is required to hold a spring stretched from its natural length of 2 centimeters to 20 centimeters. How much work is done in stretching it from 5 centimeters to 12 centimeters? For this equation, we need to use f of x equals kx, which is Hooke's law. And f of x is the force, which is 100 newtons, equals the spring constant times the displacement slash how far the spring is stretched, which must be converted into meters, which ends up being 0.18 meters as 20 centimeters minus 2 centimeters, 18 centimeters divided by 100. So divide 100 by 18, or 0.18, that gives you 555.56 equals the spring constant. And the units on that is newtons per meter. Then we must plug this into the integral for variable force of W equals integral of 555.56 x dx from A to B, which is the starting distance to the ending distance, divided by 100 to get it into meters. So 0.03, because we must subtract this value from the initial natural length, and then 0.10. So we evaluate after taking the derivative, or the antiderivative. Antiderivative of that is 277.78 x squared. If you drop the 2 down, multiply that by 2, you get 555.56. And evaluate from 0.03 to 0.10. To do that, just plug in 0.10 into 277.78. And then subtract after you plug in 0.03. 277.78 times 0.03 squared. Crunch all those numbers, and we get 2.7778 minus good old 0.25, giving us an answer of, right over here, 2.5278 Newton meters is the unit, as it is force, which is also known as a joule.
So a force of 25 pounds is required to hold a spring stretched from its natural length of 1 foot to a length of 3 feet. How much work is done in stretching it from 1.5 feet to 4 feet? Alright, so we start off, we have Hooke's law in order to get the force equation. So it's f of x is equal to k times the distance stretched, which will be 2 feet, past the original, f of x we have, so force we have, and that's a solid 25 pounds. So k is equal to 12.5 pounds, 12.5 pounds per foot. And then with this, we now have our equation to drop into our equation. Work is equal to derivative from A to B of f of x dx. And then once again we have our force equation. We have the starting point, ending point, and dx. So to drop these in, it'll be work is equal to the derivative of the distance from the start, so it's 0.5 to 3, and our equation is the 12.5 x dx. And then take the antiderivative of that, so we get 6.25 x squared. And that's going from 0.5 to 3. Okay, so we drop that in to evaluate it. 6.25 times 3 squared minus 6.25 times 0.5 squared. And then with that, we get a solid answer. The work being equal to 54.6875.